Hello, welcome to the Henstitute. This is the first edition of AP Physics 2. We are going to jump right into Chapter 11 here and have some fun. Chapter 11 is all about fluids. Specifically, we're going to look at static fluids, means fluids that aren't moving yet. And in this particular lesson, we're going to try to look at density and Archimedes' principle. So jumping right in, we're going to go into density. You probably all have learned this in a chemistry class or a physical science class a long time ago. Density is just the ratio of the mass of an object to the volume of an object. One of the things that's going to be a little bit different, however, is we are going to actually use this symbol to represent density. This is actually the Greek letter rho, R-H-O. And that's going to be our symbol that represents density. It kind of looks like a P. Usually when I draw it, I kind of give it a little more of a flourish rather than just kind of come up and curve around. I usually do a little more curve like that. But anything that I usually start at the bottom and kind of come up. And M being mass here, and then big V being our volume. And so we're going to actually measure things in kilograms per cubic meter. That's going to be a little bit different because you probably learned it in grams per cubic centimeter in a chemistry class. So if you actually look at most common things, this particular table here, for example, everything's going to be a little bit larger than you're used to. For example, water. If you ask most people, hey, what's the density of water? They'll say it's 1. And they are remembering that it was 1 gram per cubic centimeter. Well, when you're trying to convert that into kilograms per cubic meter, you have a couple of things going on. You have 1,000 factor because of your kilograms, and you actually have 1,000,000 factor because of your cubic centimeters. So this is correct. It's 1 gram per cubic centimeter, but if you notice the number they are actually throwing out, they write it in scientific notation, but it's 1,000 kilograms per cubic meter. So if you ever want to convert from grams per cubic meter into kilograms per cubic meter, this is a good one to remember, that there are 1,000 to 1. So it's almost like you're just dealing with the kilograms, but it's actually more due to the cubic centimeters and the cubic meters that you're actually relating this. So your liquids tend to be a little bit smaller, like ethyl alcohol and oil are less than water. That's why they float on it, whereas blood would be a little bit larger and mercury obviously quite a bit larger. In kilograms per cubic centimeter, your gases are quite a bit smaller. That's why everything is going to float above the water when you're dealing with that, whereas your solids here tend to be more dense than water. There are a few things that are not. For example, ice floats in water because it's less dense, and wood here is actually less dense. But just kind of keep in mind that our numbers are going to be so much larger than you are used to actually dealing with. So let's try to take a look at an example. Let's say that you had a person that had a weight of 690 newtons, and they contain 5.2 times 10 to the negative 3 cubic meters of blood. You're going to find that most of your cubic meters, a cubic meter is pretty big, so most of your numbers are going to be small. We're going to try to find the blood's weight and then express it as a percentage of the body weight. So a couple little things that we need to remind ourselves. Weight is actually not the same thing as mass. So if you remember your physics 1, the weight of an object is actually equal to the mass of an object times the acceleration of gravity. We're going to assume it's here on Earth, so the acceleration of gravity is going to be our 9.80 meters per second squared. I know some books and some teachers, Mr. Hodson, for example, uses 9.81 meters per second squared, which is perfectly acceptable. Most books kind of float between the two. I use 9.80 just because I have a silly mnemonic for remembering the weight. How do you find the weight? Take mass times 9.8. And so I end in the 8 to rhyme with the word weight. So don't forget that this is going to be another equation we need to relate, and this is going to be our acceleration of gravity. So actually what we start off with is we need to say the density of the blood would equal the mass of the blood divided by the volume of the blood. So if I was trying to find the mass of the blood so I can find its weight, I'm going to actually rearrange this and say the mass of the blood would be the density of the blood times volume. And once I have that, I need to look up the density of blood. Well, the reason I pointed it out here is it's back on this particular data table. It's 1060. So we've got the density of the blood as 1060 kilograms per cubic meter. Our volume here they give is 5.2 times 10 to the minus 3 cubic meters. We multiply these two numbers and we should be able to figure out what our mass is. I'm going to use my handy dandy scientific calculator just to make this a little bit easier on myself. Times the 1060. And I get that the mass of the blood is 5.512 kilograms. Right now I'm not going to worry about significant figures because I don't actually need to round anything off. I don't always round things off until the very end. So my ultimate goal is actually to find the weight of the blood. So I'm going to be taking that mass times gravity. So I'll take that 5.512 kilograms. I'm going to multiply it by 9.8 meters per second squared. That'll give me a weight times by 9.8. And I get 54.0176. Weight is going to be expressed in newtons because it's a force. So this would be newtons on here. However, now I know I don't get to keep all those numbers. I should be rounding this off to the correct number of significant figures. If I look at my original number, I only knew the volume of the blood to 2 significant figures, so I should just round this off to 2. So there's 1, there's 2. I don't get to keep these numbers, so I would just say 54 newtons. So the weight of my blood is 54 newtons, and it says express this as a percentage of the body weight of this person. So the person is actually 690 newtons. So if I want this as a percentage, they just want the weight of the blood divided by the weight of the person. So I take my 54 newtons and divide by my 690 newtons. Don't need those newtons in there. That's actually going to give me a decimal, so I'll eventually multiply this by 100 to actually turn this into a percent. Divided by 690. And I get that this is about 7.8% of their body weight. So almost 8% of this person's body weight is blood. So that gives us kind of a practice with the concept of weight, the concept of density, and seeing where we kind of fall. I have these answers still laid out. So they've done the exact same thing, 5.5 kilograms, 54 newtons, and 7.8%. So that's a little bit about density. Next up, we're going to jump into the concept of Archimedes' principle.